So hi, I'm Alex. Thanks for your flexibility to change the room so quickly. I'm a little bit exotic maybe because my times of development are a little over maybe, although I like hacking for private, but not in my job anymore. So we're doing this talk here with Elektrobit and with Kernkonzept. So 2 minutes maybe what we're doing. We are an automotive company. We started 30 years ago, and we're really doing automotive software, which was odd at that time. But nowadays, you know, software and cars are somehow way more associated. We have 2,200 people. You know, the market's growing, so we're also growing. That is not complicated. We have a global presence, and 3 years ago we have been bought by Continental. It's one of the biggest tier 1 suppliers with about 45 billion turnover per year. What do we do? Well, automated driving, of course. Every automotive software company does ADAS now and automated driving. Then we have vehicle infrastructure. So this is where I'm coming from here. So maybe you have heard of the Autosar standard. That's one thing we do. We are one of the largest providers of this kind of software. This software is used in nearly everything you can find in a car: braking, steering, motors, you name it. Every ECU is in there. It's functional safety relevant, of course. I mean, steering and braking is obvious, but many other functions in the car are also safety relevant, like putting an LED warning on, or if you have a head-up display, not giving out too much light so that you can actually see something, right? So there are many safety relevant functions. Then we have a connected car, so that's the typical over-the-air things, but also online monitoring and incident monitoring. That becomes more and more relevant now. User experience, so we have a navigation system. It's if you drive an Audi, maybe you have seen one of systems. We do consulting and testing. Okay, so that was the company advertisement. This is now the times where we're living in. When I started, the automotive software market was kind of slow, unestablished, but today we use machine learning and crowdsourced data in maps and other things. We connect the car with traffic lights and infrastructure. We give third-party access, so we can deliver parcels into the car. We have fleets that car to come and car to go. Personalization, yeah, everyone wants to have his personal BMW or his personal Mercedes, and then goes to the next car, just inserts his phone or USB stick, and everything configures so that is his personal style. Music's still available. Shortened development cycles, that has happened in the mobile industry way before cars, but nowadays really the development cycle for cars has become way shorter than it has been. We get something really interesting, that's evolution after SOP. Over-the-air update really means that the software in the car will change over its lifetime, which is also something really new with all possible consequences, like how does a regulatory body say this car is still fit to drive on the road? And new topics, new business models, that's the typical, we do IoT, and at the end of the presentations they say, but we don't know how to make money with it. So let's roll out all the devices and let's see, you know, where the money comes from in the end. And this happens all at the same time. Yeah, so this is a question now for you. Oh, sorry. The point is, if you go to a traditional car vendor, or OEM, they have their wheels, right? And they think now we put the mobile phone on the wheel. And the other point is, a software company says we have the mobile phone, we just put wheels on the phone. So wheels basically an app or something like that. So which one is more important? What do you think? Where to start? The mobile or the car? No comments? Robin, you? It's a trick question. Yeah, I have 2 trick questions for you. So the point is, we need to really rethink the complete electrical architecture in the car. We get domain and zonal architectures. We get centralized computing units because we don't want to put more and more functions in the car. And with each function, you add a small new computer. That's way too expensive. We need super cool networking. So that's why we get Automotive Ethernet and TSN. And we need to connect the vehicle with other ecosystems, especially the cloud. So the point is cloud and mobile first. And that is something, this is a message I'm trying to get through now for, I don't know, 3 years or so, but the point is the cloud has won and open source has won. It's just a matter of how long it takes for the domain to realize that. So here's a second question, maybe that's easier for you. You have a phone and you have a cloud, or let's say you have a phone and a vehicle. Which one needs to be more secure? You're laughing, you don't know? No personal opinion? Anyone?
I would say that depends on if the vehicle and the cloud are tied. Depends on the relationship, especially with regards to the navigation between all three, from a security or safety standpoint. Like where is the decision making taking place? Is it taking place in the vehicle? Is the training done in the cloud that is fed?
Okay, so you don't give any clear answer. Good. Summarize that. So the point is, if you talk to car producers, they say, of course, the car, right? And that's why for them it is a really tricky question. But what they don't realize is, and this is where I start, then I start explaining them how many security technology is already included in mobile phones. And then they see, okay, that is interesting. So the point is, cloud and phones are state of the art, and it's not cars. And that is an important message. It is not easy for a car manufacturer to, swallow that pill, right? So, that's for the trick question. But the point is really, it's not easy to say, because you have all your personal data on the phone. So your car can be stolen, but maybe your data is worth more than the car. Who knows? So this is what's changing currently, and this is why we're also here at Linaro Connect. This is where we are today. It's a domain architecture. You can think of this is the powertrain, or this is the infotainment system. And this is how all these companies are structured. So the internal structure of the company reflects what you put into a car. It's also the whole supplier ecosystem. All that is aligned here with domain architectures. What we're now building, and it goes on the road end of next year, is a centralized architecture. So many functions are put on one performance SoC, and most of the network is transformed into an automotive Ethernet, which leaves, let's say, traces of traditional things like rest of powertrain, rest of braking, and these kinds of things. This is for the OEM a super important step, because the whole supply structure will change, the whole software structure needs to change. All the functions in the car need to be reprogrammed. And a car has an enormous amount of software in it today. So a car has probably, no, not probably, there are numbers, I question those numbers, but if you Google it, you will find that some people say that we have now more than 100 million lines of code in a single car. And that is a huge number if you want to change the system from domain to centralized architectures. So in the future, we will see zonal architectures. That's here on the right side. So we have one big computing thing, and everything else just a smart actuator, smart sensor, which is reachable over Ethernet. And then it becomes kind of cloudy, right? And that is when the cloud technologies came in. So that is this is the storm I'm personally in, and I have to manage with my company, right? This is the logical structure. Well, we don't do that. I don't think we have the time, so you can have your session then. So some aspects of what we're currently building, and you immediately see the idea why we're talking with Linaro about maybe making a reference platform. Let's see how far these talks go. So this is what we are currently building. It's nothing more than a performance SoC. We have here you have safety cores. So let's take a Renesas or an NXP or a Texas Instruments chip. You always have these kind of classical performance, classical ECUs here. And this is where we come from. So we have an established Autosar OS. So you can put safety on it, currently an ASIL B or an ASIL C. Then we have a security part. That's basically a trust zone, of course extended maybe with secure elements. That depends on the OEM and the country you're in. And here it gets interesting. This is why we're talking today. This is the hypervisor. Michael will present a few slides about that. And again, it is a mixture of classical ECUs and modern adaptive Autosar, right? I want to show you a little picture of what is that and what we're doing. So this is, if you see, this is when product management comes. It replaces everything with our product names. What is interesting for you is that here we try to, in the performance part, provide our own kernel and our own root file system, right? Why this whole setup is interesting, you will see when I talk about the safety part. Okay, this is adaptive Autosar. Who has ever seen an Autosar architecture? 1, 2, 3, okay. So that is now adaptive Autosar, completely different than classic. It is a middleware with the things you expect in a middleware. So basically what is important here is time synchronization for, let's say, ADAS applications. If you have multiple cameras, radars, LiDARs, you want to make sure that you know that when the data has been produced and that the data arrives at you at the same time, so you can do sensor fusion with the timestamp, so you really know what's around you. The next is execution management, basically that starts, stops, restarts, and monitors applications. Platform health management is the safety part. Then you have persistency module. Okay, you need to store something. Log and trace, that has been taken over from classic Autosar. And some modules that are not really finalized. So the classic Autosar thing was we make a standard and then we implement. And we're now much more, I want to say agile, but much more flexible. We do standardization while we're implementing, which is a very interesting thing. One thing I didn't mention is communication. So here it is based on some IP. And now we're also including DDS. And there was a talk about securing DDS today here. And the classic management, this is diagnostic management, is really what you have in a classic car. So if you have these LEDs going on telling you something's broken, right? These are called diagnostic trouble codes. So all this handling of who produces diagnostic data is in the diagnostic management. There's an update and configuration management. So what we are also standardizing is how you update applications. And this is then used for the over-the-air companies, to actually do the updates. Okay. That's basically,
I had a question about your hypervisor. So it's a bare metal hypervisor?
Just wait 3 minutes. Most of your questions will be, at least that question will be answered. Good. So you have to keep in mind the two pictures. This is an enormously amount of software that we put in. So how do we deal? I wanted to make one slide about safety and one slide about security. Okay. So now here's the slide about safety. This is basically the adaptive part, and here you have containers where you put in your applications. So it's a fairly normal thing for the last 2 years to build containerized distributions. So nothing sexy. The point here is we have a central health manager, and that performs tasks like activation monitoring. It looks that it has been run. It doesn't run too long, it has been activated enough, all these kinds of things. You can also do control flow monitoring within these applications using the health monitor. Good. The problem is now we have a hypervisor and here are some cores missing. So what's the full picture? Because on most of these performance ECUs, you cannot place a high safety integrity level, right? It is a Cortex-A core, and currently you don't have so much choice, let's put it that way, if you want to put an ASIL on a performance core. So we have the safety island. No, that's a privilege partition. Okay, we have one partition that's monitoring the others, so that's good. And we have the classic part. And this is now the performance SoC. Think of TI, Renesas, or other processor. So basically, we do the safety monitoring based on the safety island. We monitor the privilege partition and we monitor the vehicle function part. And that is the first thing. So the classic and the adaptive world are much more related to each other than most pictures tell you, right? That's the first thing. But the picture is still not complete because you can probably do an ASIL B in this setup. But what is if you have higher safety allocations? Well, there are still classical components, so classic microcontrollers that you can use, and the classic controllers then monitor the monitor. So if you monitor of the monitor. Who's familiar with a safety topic? One person? Okay, so then this is new for you. There's a thing that's called decomposition. So you have a high safety integrity level, and you can bring it down by having two redundant, diverse function implementations that are free from interference from each other. You can use 2 microcontrollers for that. You can also do software separation. So that's where isolation techniques and hypervisors come into play on the performance part. And there's something called decomposition. So along the way, you have a very high safety integrity level you can decompose into lower safety integrity levels. And in the end, you have maybe 4 redundant things that execute functions and in the end contribute to your high ASIL. Yeah? So that's the part. Classic and adaptive are way more related. Then we have the security part, and it's also fairly standard. What is maybe new for you are the microcontroller parts. So the microcontroller parts usually have something that's called hardware security module. It has some crypto on it and random number generators, you know, the usual things, so you can do safe, secure storage. On the performance cores, that now depends on the individual SoC vendor. Basically, there's something called lifecycle management, so you cannot, the chip is in a certain state, like locked down or not locked down, or is in secure debug or not. There's hardware access protection on it. That depends on the vendor. So we have crypto, of course. And sometimes you have more than one crypto engine on the SoC, which is also interesting. I know chips with 3 different crypto engines, which is kind of, yeah. Okay, then we have a switch here on the other side. It's really important when we look at the security of the whole system that we always remember, you know, Ethernet is a managed switch network. We always need to include switches in the whole infrastructure in the whole car. So basically, we also provide the firmware for the switches that are used here. Good. So that is the hardware part, and up here it's a fairly obvious implementation. You know, we have 2-stage MMUs you find in ARMv8 processors, and containers and processors are used just like in any other popular Linux distribution. The point is how to get a safety integrity level with using Linux. It's a really interesting question. I would have liked to say more, but we're currently in discussion with other companies to really use Linux in a safety critical environment. But that's not settled and not public, so I cannot disclose that today. Okay, now going over to hypervisors. Why do we need to use hypervisors? You've seen the picture of the domain controller, the central controller, and then zonal controller architecture in cars. And the first is, of course, we need ECU consolidation. If you put so many functions on one SoC, it's highly likely that they're going to disturb each other. So we need to have lots and lots of isolation mechanisms on different levels. And each of these isolation mechanisms is responsible for a different thing, right? So that's the first thing we needed. The next one is network separation. So if you have multiple virtual machines, it may be a good idea to have a network virtual machine where you should put all the drivers, you put a firewall in, you put the filtering in, right? And you keep that separated from all the others. And the third one is we want to have mixed criticality. Mixed criticality means you have lots and lots of, let's say, performance stuff and one virtual machine that does the safety critical thing. And also that needs strict isolation. So hypervisors, I think the more cores you have and the more functions you consolidate, the more there's a need for a suitable hypervisor, right? Okay, now I come to our hypervisor experts. Michael, you want to take over? Yeah.
Okay. Hi, I'm Michael from Kernkonzept, and we are partnering with Elektrobit to provide the hypervisor part of that architecture that Alex has just introduced to you. So the EB corbos hypervisor that was on the previous slides actually is a commercial and safety certified variant of the L4Re open source hypervisor that we are developing. I only have time for 2 slides with lots of text. I'm not going through all of this, just a few highlights of what makes the L4Re hypervisor stand out and what makes it suitable for automotive applications. Well, first it provides isolation. On many levels. Just one keyword here, the L4Re hypervisor is a 2nd generation microkernel and actually a 3rd generation microkernel, and that means that it uses a mechanism called capabilities to isolate access or to provide access control to system objects. And that means that if you have a capability that allows you to access a certain kernel object, then you can access it, and if you don't have it, you can't even name it. So capabilities provide both access control and information hiding, and not providing capabilities or providing capabilities only to certain parts of the system and not to others is what provides the isolation. And in L4Re, we try to provide isolation many levels down into the kernel. So even the kernel objects that you cannot access through APIs tend to be isolated from each other, so that there's no communication possible. If you don't have a capability to a shared object, it's not possible to communicate across different partitions. Then L4Re is also a real-time system that helps with timing isolation. It provides real-time per CPU schedulers. Right now there's a fixed priority round robin scheme and also several non-real-time schemes. And L4Re provides thread migration and virtual CPU migration. So it's possible to migrate workloads from one physical core to another physical core, but it's optional. The kernel has been designed from the start as a real-time system. So it mostly runs very short critical sections with interrupts off. When it performs longer operations, then interrupts generally are on. And the microkernel has been implemented as a wait-free system so that we can provide upper bounds for execution times for everything the kernel does. Also, there's no shared state in the critical paths inside the microkernel. That means that if it performs an operation and only use regular system features without communication, then there's also no shared object that you need to touch that another CPU also has to touch that provides independence and isolation among physical CPU cores. And that also provides excellent scalability. So we have performed tests in high-performance computing setups with up to 256 cores. Is that right, Adam? And the system more or less scaled linearly up to that number of cores. Two other noteworthy features. The third one is virtualization. So we do support hardware-assisted virtualization on all the architectures that we run on, x86, ARM, and MIPS. And the special thing about L4Re is that not even the platform emulation part, the thing that emulate the features of the virtual machine, need to be trusted. These are also untrusted system components, and another virtual machine does not need to trust the emulation part or the platform emulation part of another virtual machine. Let me skip to the fourth feature. It's micro apps. Micro apps is what we call native L4Re applications. So it's possible to have applications that do not depend on running inside a virtual machine. We also have a native interface, and we have a subset of POSIX that you can use to provide trusted micro apps, apps that have a very small trusted computing base and that do not depend on any of the virtual machines running in your system. And you can use that to implement safety critical or security critical functions. Then there's also I/O virtualization. If you have virtual machines that contain drivers for devices, and these devices are DMA capable, then potentially the driver or the virtual machine can access all memory through DMA. And to prevent that, modern SoCs have an I/O memu that provides virtual addresses for devices as well. And L4Re supports that on x86 and on ARM. Also, there are lots of other networking features, or virtual networking features, so that you can create virtual networks among the virtual machines that you have running. And we support a VirtIO-based interface so that guest operating systems that come with VirtIO drivers, such as Linux, run out of the box and can be networked easily among each other. L4Re is open source, of course, and you can download it from through these links over there. It's licensed under the GPL version 2, but we also have commercial licensing available. So we are dual licensing capable. That means that if you need a commercial license or you need a special product with special features that needs to be maintained separately, you can also purchase commercial licenses. And that comes into play in the automotive market especially because their OEMs or car manufacturers rely on commercial licensing and on extra license features or extra contractual features for liability control and similar things. Despite L4Re being open source, it needs to have a central maintainership in order to maintain the certification capability that we have. And Kernkonzept, our company, provides that maintainership for L4Re and maintains it in a state that can be easily certified. Okay, I think that was my part.
Yeah, we need to be a little bit faster than anticipated. So the point is, what's the message here? A lot of this is open source, and it will be surprising to see that someone comes and says, okay, we built a car with open source components. Why can we do that? We do that now for 30 years for automotive. And the software quality levels in the automotive domain are really different from what you see in other markets. So the point is, in order to survive that as car companies, we need to build something, and I put it here. It needs high assurance security, because I think we should at least be as secure as a phone, which most cars today are not. We need long-term maintenance and operations, because cars are out there on the road 10, 15 years. And this is also a problem that not every company has. It needs to be real-time capable, so we need a real-time hypervisor, but also we need a real-time Linux. We need to have automotive safety up to ACLD. That's what our customers expect. They don't want to be killed when they go in the car. And that is the new thing, and that's why we're here. It's based on open source and well-established and well-proven implementations. And of course, we're also giving back, so this is not a one-way street. Okay. Well, that was the message. I think you have questions, or yeah, I think we have other micros. Yeah,
so I'm curious, obviously L4Re is open source and Linux is open source, so the majority of the lower level of software stack on most of these car implementations will be open source, but how much of that higher level stuff is going to be open source? Are you seeing any car companies move towards open sourcing any of the components that they develop?
That's a good point. So the adaptive Autosar part is not open source. Maybe in the future we need to, there have been discussions about that for a long time. But this is a real commercial software market. So the point is our customers get access to all the source code. They need to debug that. That is absolutely not a problem. The problem is the liability part. It's the same here. We need dual licensing for L4Re, because the traditional way to do that is the OEM gets your software and you take full liability, unlimited. And that is something which is very hard, where they just put it on the server and someone downloads it, doesn't know how it has been tested, designed, and certified.
Well, certainly you could have software where the source code is available and someone could compile it, but they would require signing in order to actually install it on a vehicle.
Yeah, so, traditionally it is not open source. I can think of many different solutions, but that would just be my personal opinion. Okay, the market currently works differently. I think this is for the car industry is a big step. And maybe it's one step, but this is already kind of revolutionary.
What were they using before? Were they using some other, like VxWorks?
Yeah, so in the classic part, the classic Autosar part, this is a real-time operating system. We do that there. This is a really extreme thing. There's no malloc, there are no third-party libraries, there's no extra, every single line of code has been written by us, so yeah.
One of the challenges with safety critical has been, at least looking at Linux as the bare metal hypervisor and CoreOS, has been the fact that you have such a long history of changes to the code base, and you have to have that sort of archive and that sort of, as you build your decomposition, you also have to look at the kernel. So part of your strategy seems to be, where your codes come from, you can vouch at least for the changes that have been made and track those. But I guess maybe, was that one aspect you looked at when you considered Linux versus your implementation?
No, it's not Linux versus. The point is our stuff runs on microcontrollers. It has an MPU.
Okay, so this is a
And-
microcontroller
right,
based. Okay,
right.
thank you for clarifying.
It's statically linked.
Yeah.
Yeah, no, it is super fast. If you compare an Autosar system with Linux, Linux is a disaster when it comes to performance, just because of, if you have these page table, all this dynamics loading 4K, and you know, in the classic world, you want to have a constant, you put the address, point there, get constant stuff done. Yeah, that's.
Yeah, I was thinking of some of BMW's work with Autosar and Linux, so, yeah.
Yeah, they work with both. Yeah.
Yeah.
Are there situations where you have to reboot the system, including the hypervisor, while keeping the critical or the partitions that are actually running the engine or whatever still up and running?
So that was the one slide I skipped, you know, because of time today. The point is the functions are separated into functions that are down and functions that are more on a higher logical level. And the engine is kept safe if you have one of these performance things or not, doesn't matter. So there will still be an ECU in the engine. For an anti-braking system, the response times are so fast you cannot put it up here. So latency is one. Latency, safety, and security are few of the criteria used to rip the traditional car functions apart, leave many of them below, right? And you can think of these things as brain, right? It's non-essential. And non-essential functions could be opening the door, or yeah, it's interesting to see this, how the car functions get separated now. But don't worry, the car will also go on if there's no online connection, right? It may not be as sexy as before, but it's still, you know, so I can say don't worry. That's our job, you know, to not wreak havoc on the population. Anyone else? Okay, so thank you, and to your session.